Okay, so we've been talking about exponents. We have a new class today. We've been talking about exponents. So the next logical step is to talk about logarithms. So let's talk about what is a logarithm first, and then we're going to go through the properties. So a logarithm is the inverse of the exponential function. So if you remember when we talked about inverses, we said a reflection of the function in the line y equals x. It undoes the exponent. The exponential function, if you remember, is 1 to 1. So we do call that reflection an inverse. Okay, if we graph it, our x and our y. This would be the exponential function. The logarithmic function. Okay, just so that you can see it better, because I opened up Desmos for you so that you can see the graph a little bit more clearly, because my drawing just didn't come out so well. This red function is your exponential function. This green line is the line y equals x, and this blue function is your logarithmic function. So you can see it actually is your reflection in the line y equals x. And if you just want to see the logarithmic function and none of these other ones, you can see this is what it looks like. So it looks very much like the exponential. And in fact, because it's a reflection in the line y equals x, the domain and the range simply switch, right? The idea is that we're flipping the x and the y. So if we're flipping the x and the y, then we would also be flipping the domain and the range, because the x's become the y's become the x's. So if the domain of the exponential is negative infinity to infinity, then the range of the logarithmic is going to be, negative infinity to infinity. And I still did this wrong over here. Sorry about that. Okay. So the range is negative infinity to infinity, and the domain would be the range of the exponential. So the range of the exponential is 0 to infinity, so that's going to be the domain of the logarithmic. So I'll put this down here again, but you can see that they just switch because the x and the y are switching. They're inverse functions. The domain of one is the range of the other. So let's talk about how this works then, and then we'll talk about the properties. So let's go through and actually find the inverse of the exponential, okay? So an exponential function is y equals b to the x. We're gonna ignore the a just to make our lives a little bit easier. The a can always go in at the end because the a is our y-intercept, so we can always just stick that in. We're gonna say our a is equal to 1. So our exponential function is f of x is equal to b to the x. So if you want the logarithmic function, okay, we're going to find the inverse. And we know that in order to find the inverse, we have a set of rules that we follow, right? We replace f of x with our y. Then we're going to switch x and y. And then we're going to solve for y. So it's a 3-step process. So if we go through and we do these 3 steps, we can start by replacing the f of x with y. So we have y equals b to the x. Then we're going to switch the x and the y. So now these are inverses right now, but we have to solve for y. And this is where our problem comes in, because we have to solve for an exponent. And we can't just raise this to the 1 over y, because then we'll get a b, but then over here, we'll get an x to the 1 over y. So that's not going to work. We need it to be a y equals. And that's the purpose of the logarithm. The purpose of the logarithm is to solve for the exponent. And this is something that you want to make sure that you remember, because it's going to help you during everything that we do with logarithms. Remember, solving for an exponent means we isolate it. I'm going to box this because it's so important. Here's how it works. It's going to be equal to log. This down here is a base. So base b of x. So that's what this looks like. So the way that we say this is y equals log base b of x. So you are in the quiet of your own home, or go into a corner and be in the quiet of your own corner if you have a lot of people living with you. And just say it, just repeat it. Y equals log base b of x. And the reason why it's important, 1, that you say it correctly, and 2, that you keep saying it, is that it'll help you when you're solving equations or when you're using these properties. You have to be able to say it correctly. So log base b, so that's important because what we're saying is that the base of the logarithm is the same as the base of the exponential. Okay, so again, something that'll just help you. The base of the logarithm is the same as the base of the exponential. okay? And the other reason why it's important is that it's log base b of x. So x is not an exponent, okay? So we don't want to say base b to the x. It's not an exponent. We want to say log base b of x because this is a function and you have to take the log of something. Log without anything means nothing, okay? It would be as if we said 3 plus. You have to know what you're adding to 3. Or 7 to the, we have to know what the power is. So the same thing is true of log. We have to know what we're taking the log of. Notice we say f of x. We're taking a function of x. Here we're taking the log of x. And this x has a name. The b is the base. The x is the argument. So let's do a little bit of conversion, okay? So we're going to go from a logarithmic function to a logarithmic expression to an exponential expression. We're going to go back and forth, okay? And we're going to do this a few times. So let's say, for example, that we have y equals log base 2 of 3. So this is logarithmic. Now we're going to put this in exponential form. So the same exact thing, we're just converting it to an exponential expression. So exponentially, the 2 is the base, the y is the exponent, and our answer is the argument, okay? So these two expressions are the same. It's just a different way of writing it. In one, you've solved for the exponent. In the other, you've solved for the argument. Now, most of the time when we're talking about exponential expressions, our exponent is the variable. So we want to solve for the exponent. Sometimes that's different. Sometimes the argument is the variable, so we're going to put it in exponential form. So what we're going to do is we're just going to make a table. And in our table, we're going to have our exponential expression. And then we're going to have the equivalent logarithmic expression. And sometimes I'll give you the exponential, and sometimes I'll give you the logarithmic. And all I want you to do is each time, just pause the video and try doing this on your own. So let's say that we have r to the w is equal to 5. So this is an exponential expression because it's in an exponential form. We can see that it's written as something to a power, so we would call it exponential, okay? So again, at this point, if you think that you can convert it to logarithmic, then pause the video, convert it, and then see if you were correct. Okay, so we want to put this as the logarithmic expression. Well, the purpose of a log is to solve for the exponent. Solving for the exponent means the exponent is by itself on one side of the equal sign. And then we are going to have log. The base of the exponential is the same as the base of the logarithmic, so the base is r. And then the only thing left is the argument. So the argument is the answer. So we would say this at log base R of 5. Notice we're not trying to solve any of this, okay? We're just converting. Let's say that we had 2 to the 6th is equal to x. So here, again, pause the video and practice. After every one I give you, pause the video. Try it yourself. So here, again, purpose of a log is to solve for the exponent. So this is going to be 6 equals. Now we have the log. The base of the exponential is 2. So the base of the logarithmic is 2. And then the only thing left over is the argument. So 6 is equal to log base 2 of x. Again, we're not solving for anything at this point. We're just going through it and converting. Let's say that we have 7 is equal to log base b of 3. So if we want to convert, we know that the base of the logarithmic is the same as the base of the exponential. So we're going to have b. And then the whole purpose of a log is to solve for the exponent. So the exponent is what's all by itself on this side of the equal sign. So it's b to the 7th. And then the argument is equal to our answer in the exponential. So b to the 7th is 3. If we have y is equal to log base 8 of 15, the base of the logarithmic is 8. That's going to be the base of the exponential. The whole purpose of a log is to solve for the exponent. So the y is what we've solved for here. So y is the exponent. And then the argument is our answer. If we have 2 is equal to log base 4 of 16. So notice what's going on here. The base of the exponential is the same as the base of the logarithmic. So we have 4. Purpose of a log is to solve for the exponent. So the solve for is 2. So it's 4 squared. And what is that equal to? The argument, which is 16. So notice this is what the log is saying. The log is saying, what power do we raise the base to in order to get the argument? We raise 4 to 2 to the second power, and that gives us the 16. So we're going to do 2 things at once here. We're going to solve some logs, but we're also going to convert it to exponential. So let's say that we have, I'm going to leave the left side blank. Let's say that we have log base 3 of 27. So we're saying, okay, well, what power do we raise 3 to in order to get 27? In other words, we're saying 3 to what power is equal to 27? We need to fill in this power here, okay? This is what needs filling in. So 3 to the 3rd is equal to 27. So this is a 3 here. Okay, and that is something that you should know at this point, because we said that you should learn your cubes, 3 cubed excuse me, 4 cubed, even 5 cubed. So that's something that you should just know. But you could go into a calculator and you could say, okay, what's 3 to the first? What's 3 to the second? 3 to the third? Let's figure out when we get 27, okay? If we take log base 2 of 32, and we want to know what that's equal to, what we're saying is 2 to what power is going to give us 32? And you should be relatively familiar with your powers of 2. This is 2 to the 5th, gives us 32. Okay, so some of these logs are integers. Now, if we had said log base 2 of 30, then this would not be 5. It would be 4 point something, and that would be harder to figure out. So we don't know how to do that yet, so don't worry about that. Nobody's going to ask you to evaluate log base 2 of 30 at this point. That'll come later when we start doing equations. Okay, so now let's go through the properties of logs. Now, exponentials, okay, exponents had like 8 properties. There were a lot of properties. Logarithms only have 4, okay? And the last one, we don't even use that much. So let's go through and let's go through the properties. Now, first, before we do that, I should mention that a log, I'll put this in a different color. This is just has to do with defaults. You know how if we have a radical and there is no index, it means that there's an index of 2. If we have an exponent, if we have like an x and there is no exponent, it's x to the first. We have the same thing for logs, okay? If there is no base, base 10. So in other words, if you just see the log of x, it's really log base 10 of x. We don't put in the 10. And the reason for that is that 10 is actually the most common base. We work in base 10. That's our whole number system. We have 10 digits, 0 through 9. Why do we work in base 10? Because way back when, before we had our whole math system, how did we count? We counted on our fingers. And we counted on our fingers. We have 10 fingers, 10 toes. Okay, that's where base 10 comes from. And now, like you can see with the metric system is in base 10, right? You have your meters, your kilometers, your centimeters, your nanometers, your millimeters. Everything is based on powers of 10. So base 10 is what we work in, and it's used most commonly, which is why if there is no base, it's base 10. The idea is that because it's so common, we don't want to have to write it every time. The thing is that there's another base that's very, very common, and that's base E. Okay, so e to the x is called the natural exponential log function. We talked about this in the last lecture. In the last lecture, we talked about E, and we said that that's for compounding continuously, so we call it the natural exponential function. One of the reasons is that if you take something and you have no interference, no man-made interference, if you just let your money sit there and compound and you don't withdraw and you don't deposit, it'll grow at this exponential rate of E. If you have a population and you have no man-made interference, so no murder, no crime, nothing that's going to kill people, it'll grow at a rate of E. So the natural exponential function is very common. The problem is that if we just said, okay, well, if it's a base of E, we don't write the base, then how are we going to know whether it's a base of E or if it's a base of 10? So in order to take care of that, we use different letters. Now, the fact that we use different letters doesn't make any of the rules different. Everything is the same, so, because it's still a log. So log base e of x, instead of writing the base of e, I'm going to make that look a little bit clearer. Log base e of x, we write as ln of x, and we call this the natural logarithm. And there are lots of reasons that we call it natural. Some of them require calculus, so I'm not going to go into it, but log base e of x, if you see ln, okay, we pronounce it as ln, but we don't we pronounce it as ln, but we don't write it as ln. Okay, and you have to write it with, this is an L, it is not an I. Do not write an I, so you shouldn't have a top and a bottom. This is an L, so it's ln of x, okay? Ln of x is equal to log base e of x, okay? And again, it's because we need to use this, because if we just left out the base, then we wouldn't know, is it base 10 or is it base e? So those are just some things to remember, and the properties that we're going to talk about, they apply to log in the same way that they apply to ln, okay? So let's go through and write out the 4 properties. So I'm going to write them out first. We're going to prove 1 or 2 of them. We'll prove 2 of them. There is no particular order to these properties. The last one we're actually not going to be using for a while, or not in this lecture at least. So the first property says log base b of x times y is equal to log base b of x plus log base b of y. We refer to this as the product property. And this is not surprising. It's just like the property for exponents, right? B to the x times b to the y is equal to b to the x plus y. This is very similar. When you're multiplying, it turns into addition. So this side, and we'll go through this afterwards, this side is the condensed form. This side is called the expanded form. So I'll write that down in a few minutes. Okay. The second one is kind of intuitive because it's based on this one. It's saying if instead of multiplying, you're dividing, then when you break it up, you subtract. And we call this the quotient property. Again, in exponents, if we're dividing and we have the same base, we subtract the exponents. So here, we're dividing, we have the same base, we subtract the logs. So we're going from 1 log to 2 logs. Okay. The third one says if you have log base b of x to the a power, this is an a. I don't want it to look like a 9. Let's actually use a different letter. Let's use the m power. Just because I don't want you to get confused by, is it a number or a letter? What we can actually do is we could take this exponent and we can move it out to the front and make it a coefficient. Okay. This is called the power property. And then our fourth one is kind of intuitive. Again, we're not going to use this until we get to equations, which is the next lecture. But this is saying if log base b of x equals log base b of y, then b is equal to y, and vice versa. So if b is equal, sorry, not b, x is equal to y. And vice versa, if x equals y, then log base b of x equals log base b of y. So it works in both ways. If we know that x is equal to y, okay? If we know x equals y, then we know that the logs are equal. And if the logs are equal, then we know x equals y. And notice that the bases are always the same, okay? If we have log base 3 of 7 plus log base 2 of 8, we can't combine, okay? We can't condense. It's got to have the same base. Different bases, you just leave it. Just like in exponents, if you have different bases, you can't combine the exponential expressions, okay? Let's do a proof of the product property and a proof of the power property, okay? And there are actually two ways to prove the power property. We're just going to prove it in both ways. And then we're going to do some applications where we simplify expressions. So our product property is log. I'm just going to flip this. I'm going to flip what's on each side of the equal sign. So the way that we're going to start this is we're going to set log base b of x and log base b of y to a variable, okay? We can do that. We can always set something to a variable. As long as we're not breaking any rules, we can do whatever we want. So we're going to say let m equal log base b of x and let n equal log base b of y. Now what we're going to do is we're going to turn these into exponential form. So when we switch them to exponential form, we get the base is b, the power is m here, right? The purpose of a log is to solve for the exponent. So the power is m. And what is that equal to? X. I'm going to pause the video. Hang on 1 second. Okay, sorry about that. Okay, so our next step here is to convert this to exponential form. So we have b to the m equals x. Remember, the base of the exponential is the same as the base of the logarithmic. Now we're going to do the same thing with the other one. B to the n is equal to y. Base of the exponential is the same as the base of the logarithmic. We solved for the exponent, so n is the exponent, and the argument becomes the answer, okay? Okay, so now we're gonna multiply these, and the reason why we're gonna multiply these is because we multiplied here, so we kind of just want to see what happens, okay? So I'm gonna move this up here, just in the interest of space, and we get b to the m times b to the n, and that's equal to x times y. So if you notice, now we have an x times y over here and an x times y over here, okay? But we can combine these because b to the m times b to the n, we have the same base, so we can add the exponents. And all we have to do is turn this back into logarithmic form. So if we turn it back into logarithmic form, we're going to say log. The base of the exponential is the same as the base of the logarithmic. So log base b. The argument is the same as the answer. And the purpose of a log is to solve for the exponent. So we put it back into logarithmic form. But we know what m and n are. M is equal to log base b of x. N is equal to log base b of y. So we're going to substitute back in. So we're up to our therefore statement. Log base b of x times y is equal to log base b of x plus log base b of y. And this is our QED. We're done. Okay, so let's just go through and write out what we did here. So we had our let statement, okay? Then we put our logs in exponential form. Okay, from there, what we did is we took these and we multiplied them. So we multiplied x and y. From here to here, we used the fact that, I forget how we wrote this. We might have used b to the x and b to the y, so I don't want to use the same thing. So I'm going to say a to the, I just want to use different letters, that's all. A to the w times a to the v is a to the w plus v. We were just using this law of exponents, okay? And then we, from here to here, we put back in logarithmic form. And finally, our last step was to substitute back in for m and n. So we took these, we multiplied them. When we multiplied them, we can add exponents if it's the same base. So b to the n plus n equals x times y. Then we took this exponential expression and we put it in logarithmic form. We made it into a logarithmic expression. This was the base of the exponential, so it becomes the base of the logarithm. This was the answer, so it becomes the argument. A and A, answer, argument. This is the exponent. Purpose of the log is to solve for the exponent. Purpose of the log is to solve for the exponent. And then we let m equal log base b of x. So we're just substituting back in. We're replacing m with log base b of x, and we're replacing n with log base b of y. And this is the proof of the product property. And we're done. And if we wanted to prove the quotient property, everything would be exactly the same. This would be the same, except instead of multiplying, we would divide, which means that this would become a b to the m minus n equals x over y. So when we substitute it back in, when we turn it back into exponential form, we would have log base b of x over y is equal to m minus n. So this would become log base b of x minus log base b of y. So the only difference between the proof for the quotient form is every time that you see us multiply here, you would be dividing. And every time that you see us adding here, we would be subtracting. That's it. Otherwise, it's the same proof. Okay? Okay, let's do the proof of the power property. So there are two ways to prove this. So this is saying log base b of x to the m is equal to m log base b of x. So the first way to prove it is we can use the laws of exponents, the definition of exponents. So we could say log base b of x times x times x this is all correct, okay? I'm just gonna add it. I'm just gonna write it so that we can say that this is equal to log base b of x to the m. So that it's clear. So we're doing exactly what we did with the exponents. We're showing what the right side is, what the left side is equal to, and then we're going to show that that's the same thing as the right side. So this is happening m times. Okay, this is just definition of exponents. Right? X to the m is the same thing as x times x times x m times. But then this could be rewritten using this law right here, which we just proved. So this is equal to log base b of x plus log base b of x. We keep going, plus log base b of x. And there were m x's, so this is happening m times. And this comes from log base b of x times y. It's saying we can split it up into addition. Because of that, a short way of writing something that's being added m times is just to multiply it by m. This is definition of multiplication. QED, because we're done. The left side is equal to the right side. Okay, so that's the proof of the power property. There is another proof. If you're interested, just send me an email and I'll show you the second proof. It's a little bit more like this one up here. Okay, I just don't want to take the time in this video. But there is another way to prove the power property.